Well, welcome everyone. And first of all, I would like to thank the organizers for the opportunity to talk in this nice conference and share some of the work we are doing at Universitat Politécnica de Catalunya to investigate some of the uses of cold atoms to access some exotic phases of condensed matter that are challenging to measure experimentally. So the system I will focus on today are neutral atoms in the presence of an optical lattice formed by a retroreflective beam. So at low temperatures, these atoms get trapped at the minima of this lattice, but still they can hop from one side to the other thanks to quantum tunneling. So this gives you some kinetic term for free. In addition to this, when you have several atoms and two of them appear in the same site, there are collisional forces that provide you an on-site interaction. And this combination of on-site interactions and tunneling motivated the first uses of these platforms as analog simulators in the field of condensed matter, because this is a natural encoding of the Bose-Hubbard Hamiltonian, which is a toy model for superconductivity. And if you look into the phase diagram of this model, at low temperatures, you see that the ground state follows a phase transition between a mute insulator, where the on-site interactions dominate, and atoms want to be as far apart as possible, to a superfluid phase, where the atoms spread, the kinetic term wins, and there is a well-defined momentum in these bosons. So the way this was experimentally measured in the early 2000s was by playing some trick, which is once you have the state you want to measure, you release the trap, the atoms expand ballistically, and you are taking effectively a measurement in reciprocal space, which allows you, for example, to measure these interference patterns that reveal the presence of a well-defined momentum in the superfluid phase. So since then, 20 years have passed, and experimentalists have been able to play a lot with these systems, not only with bosons, but also with fermions and even atomic mixtures, where they have been able to explore many rich quantum physics in the context of condensed matter, for example, the presence of vortices, polaron physics, etc. And part of this successful history in the atomic community is now expanding to other fields of physics, because the exquisite control of these systems and the ability to even measure nowadays the presence of atoms in each individual side of the lattice is now helping in other areas. So atomic simulators are now expanding to the field of studying exotic phases of matter, such as topological states, but also high energy physics, where current efforts being put in the study of lattice gauge theories or even cosmology. So far, I've been talking about atoms that interact with each other when they are in the same site. So these are on-site interactions. But one could argue that many interesting physics would also appear when you allow an extra degree of freedom, which is the ability of atoms to talk to each other even when they are 2-3 sites apart. So to engineer these extended interactions, there are several ways to do that. And today I would like to just motivate some of the interesting physics that can appear when you allow this extra degree of freedom by presenting a very simple toy model. So the toy model I will focus on this hot topic talk is the following. So we'll be talking a one-dimensional system with fermions that, in addition to some antiferromagnetic order and on-site interaction, they are actually able to talk to each other to nearest neighbors. And this nearest neighbor interaction is actually very crucial because it gives you a rich phase diagram with some exotic states that appear where the natural translational invariance of your lattice is spontaneously broken. So these are the so-called spontaneously broken symmetries. And you can see that in a fermionic 1D system, there are actually only 3 of them that can appear, that can exist, and are the following. And actually, the 3 of them are present in the ground state physics of this toy model. So intuitively, when the nearest neighbor interaction wins, atoms don't want to be in adjacent sites. So the ground state corresponds to a charge density wave where atoms are just occupying even or odd sides of your lattice. So you have an uneven occupation of your lattice. On the other hand, when the nearest neighbor interaction is suppressed, atoms reach the ground state when there is a uniform occupation of fixed atoms, which appear in an antiferromagnetic order, where the spin is alternated. What is interesting is that in between these two phases, there is a frustration. And the result is that the ground state in this particular configuration is what is called a bond order wave. So this is an exotic state where the atoms are not localized anymore, but are able to tunnel between neighbor sites, but in a very particular way. they are only able to occupy some of the links of the lattice. So for example, in this case, they are able to tunnel between this link, but this link is not, there is no presence of tunneling. So here you have an even occupation, not of the charge of your lattice, but in the links. And this is interesting because this is actually a topological state that allows for the presence of a winding number and edge states. So then the question is, how can you experimentally access this? Or how would you be able to engineer this nearest neighbor interaction? Well, in this talk, we have been seeing several examples of different groups around the world which are pushing these efforts to engineer long-range interactions. So we have seen talks by Sil Nick and Julian Juan using, for example, photons to engineer long-range interactions. We have been talking about Rydberg atoms, where electrons are excited to a high energy level, and this provides strong forces. And in this talk, I will just motivate the use of paramagnetic atoms that Luis presented, where atoms, such as erbium or dysprosium, naturally have an extended interaction, extended dipolar interaction between them. So these atoms have a typical magnetic moment of 1 dBi. So you do the math, you can see that the tunneling in these optical lattices can actually compete with the nearest neighbor interaction, but with one price. These atoms need to be close enough to each other, in the order of few hundred nanometers. So these are optical lattices that are much shorter than what one usually use optically. So one of the challenges, therefore, is that in these short optical lattices of a few hundred nanometers, the wavelength is shorter than the optical transitions you would usually use for atomic gas microscopy. And this, therefore, diffraction poses a limit to use the nice tools of atomic gas microscopy to measure each individual site of the lattice and therefore extract the local order parameters that would give you a very clear evidence of the physics I presented before. So therefore, the question I will try to address today is whether one can still detect the 3 broken symmetries that can appear in 1D fermionic models, even if one doesn't have access to local order parameters. And this is work done in collaboration with our theoretical collaborators, Luca Barbiero in Torino, Maciej Levenstein and ICFO, and also experimental collaborators such as Christoph Wettenberg in Hamburg, and Sergi Julia, who is now at Pascal, and the help of my master student, Carmen Gallego, who did all the tensor network calculations I will be showing from now on. So then the challenge is the following. How can we measure this with our local order parameters? So the trick I will focus is one technique that is actually quite old, and is the use of noise correlation measurements. So the idea is that if you allow your atoms to expand ballistically after you remove your lattice, you are getting access to reciprocal space. And there you can directly look into the density of momentum, but you can also do some more elaborate measurements, for example, 2-point correlators. Interestingly, when you do 2-point correlators at moments that are separated by a fixed distance, you're actually getting these measurements that were proposed in the early 2000s, which are called noise correlation measurements. And intuitively, they give you access to the effective lattice of your state. So this was used already, for example, in 2015 by the team of Till Meslinger to measure a transition in an hexagonal lattice with fermions, where the transition between a Mott insulator to a charge density wave actually changed the effective lattice of your system from hexagonal to a square. So when you apply this equation to this kind of system where you allow for an even occupation of even and odd sites, you can actually see that some of the peaks are actually a direct measurement of the asymmetry, the uneven occupation between even and odd sites. So therefore, you have a charge density wave like this, a signal in this noise correlation measurement will reveal this presence as compared with an even occupation in this case. Therefore, if you apply just the same techniques, these noise correlation measurements would give you a direct measurement and in a spin-resolved way of the charge density wave and antiferromagnet. But what about the bond order wave? Because here there is not an uneven occupation of your sites. All your sites are occupied and you even have tunneling, as opposed to having fixed charges. So what we have seen is that you apply this equation, but now you allow the possibility of atoms tunneling from neighbor sites. There are also actually some additional contributions in your noise correlation measurements, which in addition to account for the uneven distribution of charge, they're also accounting for an uneven distribution of tunneling between even or odd links of your lattice. Therefore, if you just follow your phase diagram and calculate this noise correlation measurement at this point, you can actually see that you will get a signal in all three phases, meaning that there is a broken symmetry in all the three of them. So therefore, if you do this measurement, you are seeing that there is a symmetry that is broken, but in principle, you cannot directly tell which one, because all three will give you a signal. So therefore, can we use these techniques, these noise correlation measurements, that is a measurement that is easy to do because it's after a time of flight, to actually distinguish which broken symmetry we have? Well, for this, we propose a strategy which is combine these noise correlation measurements with some lattice modulation. The trick is the following. Imagine you are in a charge density wave that appears when the nearest neighbor interaction is strong, and they are occupying, for example, the odd sides of your lattice. If you're able to modulate the lattice, something you can do is to adiabatically reduce the energy of the even sides. And if you do this slowly, your ground state actually corresponds to the new ground state, so you can adiabatically follow it, and after some time, you will still get the same state. Nothing has changed. However, what happens if you now reduce the energy in the opposite state? Now the new ground state is occupying the even sides. And actually, you follow this path, you can see that there is a gap closing. So you cannot adiabatically go from one state to another with occupied even sides. As a result, in the task line, you see that actually the final state you reach is not a charge density wave anymore. And this is something you can also tell if you just have access to noise correlation measurements. You see that if you are explicitly breaking the right sector of your symmetry, your final state is preserved. However, if you choose the wrong sector, your final state is not a charge density wave anymore, and there is a gap in the noise correlation measurements that you get at final time. So this difference in the noise correlation measurement is telling you that the symmetry that you are explicitly breaking was already broken at the beginning. So this phase was present. So you can do this approach not only for a charge density wave, all three different phases. For example, in the case of bone order wave, the trick is that you would explicitly break the links, even or odd. And if you do that, you can recover a phase diagram, which is very similar to the one you have access only with local order parameters. So the key message is that by just playing with these noise correlation measurements that were introduced 20 years ago, you can still access to some of the exotic phases that these extended interactions are giving you, even if you don't have access to local order parameters. So just as an outlook, this is an example of one of the many opportunities that extended interactions provide you. This was in the case of condensed matter, but there are many different applications in thermalization, entanglement, building, and so on. And as an outlook, one of the applications I'm really fascinated about is the possibility of using these extended interactions in optical lattices to also help the analog simulation of problems in quantum chemistry. One of the main challenges is indeed that electrons in chemistry repel each other in a very long-range manner, as 1/r. So in this direction, we have been doing over the last years some work to identify which questions in chemistry could be relevant to address by these analog simulators, and which are the mappings and measurements that could be useful to answer those questions related to ground state physics, excited states, but also dynamical physics. So to that, I conclude by just reminding, therefore, that engineering long-range interaction is opening new opportunities for quantum simulation, not only in condensed matter, but also in many other fields of physics. And in this exploration, we should not forget the old tools we have been using for many years. So this work was done at Universitat Politécnica Catalunya, where I'm an assistant professor right now. We are in the Barcelona Quantum Group, which was originally initiated by Professor Jordi Boronat, and focused on quantum Monte Carlo. And with incorporation of some new members in the group, we are bringing new ideas and techniques. So if you feel interested about any of these, feel very welcome to approach us. And with that, I thank you for your attention.
Thank you very much. And the talk is now open for discussion.
Thank you very much for the very nice talk. You mentioned like your motivation is you want to study dipolar, so 1D dipolar system, so with so extended Bose-Hubbard model, but like the phase diagram of those 1D system is a bit like you get additional phases than just the three you mentioned.
So in this toy model, I just explore a line in the phase diagram, which is for a fixed antiferromagnetic order and a fixed on-site interaction. So it's just a line in the diagram. If you explore all the full possibilities with all the terms, maybe you get also additional.
Okay, but you didn't have a look what will those noise correlation measurements looks for other phases, Joanna?
No, here we focus on this one. So for example, you just have, let's say, a mode insulator where you have an even distribution of them, then the noise correlation measurement at this particular point would give you a 0.
Okay.
Because there is no uneven occupation of sites or links. So then in this talk, I will focus on when you get a signal, can you use this to actually distinguish between all the possibilities? Because it's not only a mode insulator that can appear, as in these experiments with hexagonal lattice. Actually, there are other 3 phases that could be being revealed by this noise correlation measurement. So then this is the motivation to try to distinguish what we are getting.
Yeah, but I mean, like in a 1D dipolar system, you can have, for example, Alden phase where you actually have those pairing that are not. So can you, what I mean is, I think it's not possible, I guess, with noise correlation measurements. Also, to my knowledge, I guess, to distinguish between them.
So this is actually a very good question. So one of the things we were doing also was trying to see which there are other phases that could be benefiting from this. And one of the ones we look actually was Halden phase.
Okay, but you have not yet.
And as far as we tried, in this case, these noise correlation measurements were not giving you a signal. Like maybe there are smarter tricks that we were not be able to find. But yeah, the intuition is that if you don't have this uneven occupation of even and odd sides or links, then maybe you need other tools.
Okay, thank you very much.
Thank you.
If there are no urgent questions, let's thank the speaker again.